All right, guys, as you saw when you did the ChemQuest 11, there is energy that's involved in changes of state. So if you change from being a solid to a liquid or a liquid to a gas, there's going to be changes. There's going to be energy that's involved in that. And we also saw a graph that looked like this, and it was kind of odd because you have these flat sections here where energy is still being added. So you're still adding heat. Like if I had a container of ice and I put it on a hot plate and I heated it up, that ice would slowly warm up until it got to be 0, but then it would be like slushy water at 0 degrees until all of that ice had melted. Right? You're still adding heat through all of that, but the temperature is not going up until the phase change finishes. Then the temperature goes up to 100, and then you have this next flat section. We call that a plateau, and it's evidence of where a phase change is happening. So you're still adding energy throughout that process, but you don't have a change in temperature. And so we need another way that we can calculate that energy change. Obviously, where there's a change in temperature, we can use that Q equals mc delta T. But then at the phase changes, we need a different way to calculate that. So we have this thing called the heat of vaporization or the heat of fusion, and we represent that delta H fusion and delta H vap for vaporization. And that's the energy per gram, or sometimes it'll be given to you in the energy per mole. So you kind of have to look at the units. The ChemQuest gave it to us in energy per gram. Some of the other worksheets that we might do might give it to you in energy per mole. So you just got to be careful of that. So in this case, since it's energy per gram, it's going to be Q equals the delta H fusion times the mass, or Q equals delta H vap times the mass. And so if we're going to do something, and I'll show you an example here in just a second, if we're going to do something where we're going to take a substance from way cold up to way hot, we have to do Q equals mc delta T, then we have to do Q equals delta H fusion times mass, and we have to do Q equals mc delta T, then heat of vaporization times mass, then Q equals mc delta T. We have to break it up into each one of those component areas. And we even see for water especially that the specific heat for ice is different than the specific heat for liquid water, and is different still from the specific heat of the steam or the vapor. And so we have to do those in different pieces because of those different specific heats. We also have to account for the energy that's involved in the phase change. Now, this is what we call a heating curve because we're adding energy. And so as you're going from a solid to a liquid, you have to add energy in order for that substance to melt. Same thing up here. If you're going from a liquid to a vapor, you have to add energy in order for that to vaporize from a liquid to a gas. We can also have a cooling curve, and that's what this is right here. We can call this a cooling curve. And it's the same idea as a heating curve, and all the numbers are going to be the same. And we'll, in fact, we still call this the heat of vaporization, even though we're going in the direction where we're cooling. So we're going from here, it's a vapor. Now it's a phase change where it's condensing down into the liquid, and here it becomes a liquid and cools down. And then at this point here, this is where the water would be freezing. And so that's still going to be heat of fusion, right? Even though it's the opposite direction. It's the same amount of energy, whether you're adding energy or removing energy. So that's something to think about, right? When water condenses from a gas to a liquid, it's got to give off energy. The same amount of energy it would have to gain in order to vaporize, it's going to give off. That's how you can get steam burns, right? You open up that pot of water, that steam comes up, it hits your face, it condenses, and when it condenses, it gives off a lot of energy. Same thing down here. As water freezes, it has to release energy. It has to give off energy. It has to have energy removed from it. And so Think about a refrigerator. A refrigerator is not making it cold. Instead, it's removing heat from it. I'm going to talk about that a little bit more in a different screencast, but you think about sweating. The sweating is the same idea, right? Sweating is liquid water that is turning into a gas. It's taking heat away from you. So there's all sorts of different applications that we can have on this. But let's look at one of our example problems. We're going to look at question number 1 on skill practice 11. And so that's one of our homework assignments, is to work through these questions here. And so we're asked, okay, if we have 210 grams of water and we're going to raise it from negative 40 degrees Celsius to 155 degrees Celsius, how much energy is involved in that? So when you start these problems, I want you to sketch out a little heating curve. And we're just going to sketch this out here a little bit. It doesn't have to be perfect. We're just trying to figure out, okay, where are we going? This is 0. This is 100 because this is water. If it was a different substance, those temperature values might be a little bit different. But basically, we're starting from way down at negative 40 and trying to go up to 155. So in this case, there's going to be 5 parts to our problem. And we're going to break it up into those 5 different parts. So part A, that's going to be from negative 40 up to 0 degrees, right? In order to do that, we're going to do MC delta T. And so the mass is 210. The specific heat of ice is 2.06. And if you look in Schoology, there's a little note sheet where that information is if you need a reminder of that. Times 40. That's our temperature change, our delta T. All right, a little squeeze for space here, but that's going to be 17,304 joules. We want to keep our units consistent when we're now going through our heat of fusion. That's our melting, right? In order to do that, that's going to be Q times the heat of fusion, or Q equals the heat of fusion times the mass. So the mass again is 210. Heat of fusion in this case is 334 joules per gram. So that's going to give us an answer in joules. Sometimes we end up with an answer in kilojoules if our heat of vaporization is given to us, or our heat of fusion is given to us in kilojoules per mole. So just be mindful of that as you're working through some of these problems, that we want these units to be consistent here. Part C, you're going to heat it from 0 up to 100 degrees. Again, that's MC delta T. So 210 times 4.18 times 100. Right, that comes out to be 87,780 joules. Part D, that's the flat line, the plateau. That's where we're going to vaporize. So that'll be the mass times the heat of vaporization. Heat of vaporization for water is 2,260 joules per gram. So that's 474,000, holy cow, 600 joules. You see that most of the energy in the case of water is involved in the phase change. There's a lot of energy involved in the phase change of water, whether it be heating that water up to be a vapor or cooling it down. And in fact, that's how thunderstorms work as well. You think about all this warm water that's evaporated down the Gulf of Mexico, and then it comes up our way in the springtime, and you've got that warm, moist air that's then colliding with cold air, and it's condensing, it's releasing a lot of heat. That's how thunderstorms develop. There's a lot of energy in there because of the energy that's contained in the water. The last piece here, part E, is where we're going from 100 up to 155, so that's going to be MC delta T. So 210 times the specific heat of vapor, 2.02, times the 55 degrees is 23,331 joules. We then add all those up, 673,155 joules. We then want to apply sig figs. If I go back in my original measurement, I had 210, which is 2 sig figs. I have negative 40, which we're going to take that to be 2 sig figs, even though normally 40 is not a sig fig. But oftentimes with temperature, even if it's that decimal point's often not included for whatever reason. It's poor practice, but if we have a temperature that's like 10, 30, 20, we can assume that to be 2 sig figs. So we really need to have 2 sig figs in our answer here. So that's where the 670,000 joules or 670 kilojoules would be our final answer. So the key is, as you're doing these, break it up into these individual parts, right? Identify the parts that you need to do first, then go ahead and do the calculations. And I really want to see those little sketches on the side of your paper that show that you're doing, you're breaking it up into the individual pieces.